Welcome back. So in previous class, we have seen that what are the different pull-up devices we can use as in the MOS inverter diagram, MOS inverter case. And we studied the operation of an NMOS inverter with resistive load, an NMOS inverter with depletion NMOS transistor as a load, an NMOS inverter with enhancement transistor as a load, its a characteristic curves, the drawbacks and of each and every case we have seen. Now let us see the operation of CMOS inverter, that is an NMOS inverter with PMOS as a pull-up device. PMOS as a pull-up device. The resultant circuit is called CMOS inverter. CMOS inverter. The first diagram is the CMOS inverter diagram. Okay. The last one is the inverter characteristics and the flow of current between VDD and ground. Let us see first of all whether this one work as an inverter or not. For that, first of all, I am applying logical 0 value at the input. That is 0 volts I am connecting at the input. With the 0 volts, the state of pull down transistor is in half state, whereas the state of the pull up transistor in on state, because these two are the complement transistors, right? One is PMOS and another one is NMOS. If one transistor is in on means definitely other transistor in the half state, right? Now with 0 input, the pull down transistor is in half state, whereas pull up transistor in on state. Hence the output voltage is a open circuited voltage because the pull down transistor acts as a open circuit because it is in half state. So the output is a open circuited voltage. You know, open circuited voltage means a maximum voltage almost equal to VDD, almost equal to VDD. That high VDD we are getting. See in the characteristics also, at low input voltages, high VDD voltage we are getting at the output. So with reference to case 1, it satisfies the inverter the inverter operation. What is inverter operation? Always the output is complement of the input. Similarly, let observe the operation applying the logical 1 value at the input. Logical 1 means a VDD voltage we are going to connect at the V input. With that input voltage at the gate of NMOS and PMOS transistors, the state of NMOS transistor is in on state, whereas the state of PMOS transistor in half state. So that the output is a short circuited voltage because the NMOS transistor in on state. On state means it acts as a short circuit. The output is a short circuited voltage. Short circuited voltage is 0 volts almost. Okay. Therefore, see the diagram. If the input is VDD, output is 0 volts. The output is 0 volts. Very perfect voltage levels we can get at the output with reference to logical high and with reference to logical low in the CMOS inverter case. Okay, it definitely with this applied inputs, always the output is complement of the input. So it definitely work as an inverter and it gives perfect voltage levels at both logical high output and logical low outputs. That is the one advantage of this CMOS inverter. And another thing is, if you take either logical low output or logical high output, only one transistor is in on. Only one transistor is in on. Therefore, there is no direct current flow from VDD to ground. Therefore, no static power dissipation. There is no static power dissipation like whatever the static power dissipation we observed in MOS inverter with the depletion MOS transistor, enhancement transistor case. We have seen that there in the output low case, a short circuit current flow between VDD to ground. Because of that current, the power dissipation is high. Here there is no direct current flow between VDD and ground. That's why the power dissipation is very less. That is, the static power dissipation is very less, almost zero, but when the transition appears, that is, the output is changing from logical high to logical low, when the output changed from logical high to logical low, or logical low to logical high, or in the characteristic curve, when the output changed from logical high to logical low, at certain instant, the both the transistors are in on state. Both the transistor are in on state. Why? Because one transistor goes to on to half, whereas another transistor goes to half to on. That's why there is a instant both the transistors are in on state. There a short circuit will occur between VDD and ground. So short circuit current flow we can observe. So the resultant power dissipation is short circuited power dissipation. But it is occur at a very finite time. You can see in the diagram also, this is the current characteristics of this CMOS inverter. Okay, the maximum current flow occur at this time instant. Okay, at this input voltage maybe. Okay, so only in the transition period, at particular instant, the power dissipation is occur, that is called the short circuited power dissipation. This is the drawback. In this CMOS inverter case. Okay, so with this, the conclusion with reference to CMOS inverter is there is no static power dissipation. Okay, full high and low levels are generated at the output. That is, the voltage levels are perfect with reference to logical low and logical high. And CMOS circuits are ratioless. That means ratioless means perfect symmetrical characteristics you can observe with reference to this inverter, that is CMOS inverter, rather other type of inverters. Okay, that is about the CMOS.